Hello friends, so far we have been discussing the response offered by metals and alloys for different combinations of or different mechanical conditions. The reason we focused on metals and alloys is because when you consider uniaxial tensile loading, so we began with our discussion with uniaxial tensile loading. When you consider uniaxial tensile loading, the response offered by this category of materials, that is metals and alloys, can be expressed schematically by considering the response and the mechanical condition that offers or that brings about this response in a graphical manner. And when you consider the load, that is the mechanical condition that we impose under uniaxial tensile loading along the y-axis, and the elongation, the change in the longitudinal dimension along the x-axis, generally the metals and alloys would offer a behavior that can be described in this manner. Now, we also saw that it is possible for us to replace this load with stress and the elongation with strain. Even we are able, if we replace the way we describe the x and y axis, the trend that we observe in metals and alloy is going to remain the same. Now, from this particular description of the mechanical behavior of metals and alloys, we found that there are certain limitations to this description. This description does not completely represent the entire response that we observe in a given sample, meaning when you impose a uniaxial tensile loading, in addition to the change in the dimension along the loading direction, there is also a change in the dimension in the direction perpendicular to the loading direction. So if you consider the loading direction to be the longitudinal direction, we saw that there is also a change in the dimension along the lateral direction. So this we refer to as the Poisson's effect, and we wanted to quantify how, or we want to have a parameter to quantify or to describe the response under uniaxial tensile loading that includes both the change in the dimension along the loading direction and also in the perpendicular direction. For that, we introduced the Poisson's ratio, a parameter called Poisson's ratio, that includes both the change in the dimension along the direction or along the loading direction and also along the direction that is perpendicular to the loading direction. If our loading direction is longitudinal direction, then and the perpendicular direction will be the lateral one, the Poisson's ratio will be the strain along the lateral direction to that of the strain along the longitudinal direction. There is a negative sign associated with the Poisson's ratio because along the lateral direction, the dimensional change that we observe can also be brought about by the compressive loading, or when you consider the stress the material experiences along the lateral direction, the direction perpendicular to the uniaxial tensile loading, it is a compressive stress. So therefore, we have a negative sign associated with the description of the Poisson's ratio. Now, when we consider also the condition, the mechanical condition that is associated with this stress strain curve or the load elongation curve, it is a rather straightforward imposition of, or the straightforward implementation of the tensile loading. We have imposed the tensile loading in a rather straightforward manner along a single axis alone. So therefore, we moved away from uniaxial tensile loading to biaxial tensile loading, wherein in addition to the longitudinal direction, we also impose the tensile loading along one of the lateral directions. So there are two axes, along two axes we are now imposing the tensile loading, and because of this rather convoluted loading condition, we now have a response that is not as straightforward as the one that we observe under uniaxial tensile loading. In case of biaxial tensile loading, the response that we observe is a bit more elaborate than the one that we observed during uniaxial tensile loading. And from biaxial tensile loading, we moved to a triaxial condition, a triaxial tensile loading condition, wherein we were able to describe the response offered by the material in a generalized manner. So this response under triaxial tensile loading, the response offered by the material, the dimensional change that material exhibits under triaxial loading is governed by all these three stresses. So in triaxial tensile loading, we are imposing the tensile load along the three direction, and along a given direction, the response offered by the material is influenced by all these three stresses that we impose. However, all these three stresses do not contribute equally to the response that we observe. Now, if you consider the expression of the response, the strain along a particular direction, say x, for or under triaxial tensile loading, the expression will be of this form. So we can express the response offered by the material along the x direction under triaxial tensile loading in this manner. Sigma x minus the Poisson's ratio sigma y plus sigma z. So here the sigma x is the stress that we impose along the loading direction. So it is along the loading direction. However, sigma y and sigma z are the stress that we impose perpendicular to the loading direction. So therefore, the influence offered by the stress along the loading direction. So we are considering the response along the x-axis. Now the influence offered by the stress along the same axis. So we are interested in the strain or the strain along the x-axis, though the influence of the stress along the same axis is different from the influence of the stresses along the perpendicular direction. Because if you consider this expression, the influence, the contribution of the stress along the same axis is being proportioned by the ratio of 1 by E. So the amount of contribution the sigma x makes to the epsilon x, that is the stress along the same direction makes to the corresponding strain, is proportioned by 1 by E. Whereas the amount of contribution the stress along the perpendicular direction, that is y and z, it makes on the strain along a given direction is proportioned by this ratio, that is nu by E, that is the ratio of the Poisson's effect and the Young's modulus. So therefore, even though all the three tensile stresses they contribute to the response offered by the material, the amount of contribution they make vary, and in one of the cases when the strain direction and the stress directions are the same, the contribution is proportioned based on the ratio of 1 by E, that is 1 by Young's modulus, whereas in case of the stresses along the perpendicular direction, their contribution is proportioned based on the ratio of the Poisson's effect and the Young's modulus. Now, in the previous lecture, instead of describing the stresses or particularly the response offered by the material by focusing ourselves or aligning ourselves on a specific direction, we saw it is also possible for us to describe the response offered by the material by considering the material as a whole, by considering the material completely in its totality. So by what we mean by considering the material in its totality is by considering the volume, change in the volume offered by the material when we are imposing the mechanical condition. So this ultimately led us to describing or identifying a specific material parameter or property called bulk modulus. This bulk modulus is similar to that of our Young's modulus, but the only difference is the bulk modulus, it considers not the change or not the response offered by the material along a specific direction, but the bulk modulus considers the complete volumetric change that we observe. The volumetric change that we observe when we are imposing these mechanical conditions within the elastic region. So we are focusing on the elastic region, we are restricting ourselves to the elastic region, and we are imposing different mechanical conditions. And under these different mechanical conditions, instead of describing the response by focusing on a specific axis alone, we are describing the response by considering the overall change in the volume of the material when we are imposing these conditions. Now, when we arrived at or when we made the discussions on all these different aspects, or when we considered or when we moved on from one mechanical condition to another mechanical condition, and when we moved on from one way of describing the response to another way of describing, when we augmented upon the existing way of describing the response, that is instead of longitudinal response alone, when we considered both longitudinal and the lateral responses, there still is one form of the mechanical condition. Even though we are talking about different mechanical condition, we are generally associating ourselves with one form of mechanical condition. So that form is, even though we are talking about different responses and why these different responses arise for different mechanical condition and how it can be quantified, when you consider the nature of the mechanical condition, the nature of the mechanical condition is principally tensile loading. So the different conditions that we have considered thus far, the different types of conditions and the different ways the response offered by the material varies with this condition, even though these are different, one is different from another, but principally the nature of the condition remains the same, that all these conditions as thus far we have been considering is or as being the tensile loading. Now, even though the expression such as this, which we arrived for triaxial tensile loading, it can be translated to, or it can be based on this expression, it will also be possible for us to arrive at the corresponding response for the compressive loading. So only deviation or only change that we can make or only extension that we can make from whatever we have considered so far is an extension to compressive loading. So principally our discussion has largely been confined to tensile loading. However, since we have arrived at the numerical expressions for how the material would respond for a given combination of tensile loading, for given a triaxial tensile loading, from this expression we will be able to extend what will be the response for the combinations of both tensile and compressive loading, and also what we would get, what would be the resulting response when we have just the compressive loading alone. So all we need to do is we need to consider appropriate convention and substitute the appropriate stresses here. So here in this expression we have three different stresses and we have thus far assumed it to be three tensile loading, and when we introduce the appropriate convention, then it will be possible for us to consider the combination of both compressive and tensile loading, or exclusively triaxial compressive loading is also possible. So whatever expressions that we have derived, whatever discussions that we have made so far for the tensile loading will also be applicable for the compressive loading, as long as we are able to translate or as long as we are able to incorporate the appropriate conventions. So generally speaking, all our discussion have thus far been confined to principally to tensile loading, and as it is, it can be extended to compressive loading. Now, if you consider what is the similarity between the compressive and tensile loading? So when you consider the nature of these two loading conditions, it is possible for us to describe by looking at the way these conditions or these mechanical conditions can be imposed. So we have considered, we have made some discussions, but I have rather extended our discussion from the simplistic case to a bit convoluted case. We have started with uniaxial tensile loading and uniaxial loading condition. We have moved to the triaxial loading condition, and instead of considering the response along a singular direction alone, along a particular direction alone, we have moved to a holistic consideration of the response, a volumetric change in the material as we impose these mechanical conditions. Despite all these, we now identify that our discussion has been confined to one form of loading condition, that is tensile loading, and owing to our understanding of how the compression load is treated or compression stress is treated numerically, we saw that it is also possible for us to translate whatever expression we gained through tensile loading to compressive loading. So since we have arrived at expression for tensile loading, it is possible for us to translate it to any combination of tensile and compressive loading, or for exclusively the compressive loading alone. So far we have arrived at this. Now what we want to do is we want to understand, or we want to change our focus. We want to move away and focus on different forms of loading conditions as well. So before doing that, we want to know what is the similarity between the tensile and compression loading, and how would the new loading condition that I need to focus will be different from these two. So when you consider the tensile and compressive loading, the way we impose it. So if you consider a simplistic way of imposing it, we usually, the tensile testing machine, or the way we describe the tensile stress that we impose is of this form here. So we are imposing, when we have the loading direction that is indicated in this way, then it means that we are imposing a tensile loading. Now the same kind of loading can be achieved. So the same kind of loading, an equivalent form of this loading, can be achieved when we fix one of our longitudinal ends. So what we are doing is we are fixing one of our longitudinal ends. So we are fixing this longitudinal ends. So once you have fixed this longitudinal end, now all we need to do is we need to impose the load along this direction, and this will correspond to the tensile loading. So the tensile loading, the generalized way of representing it would be the load along in this case the longitudinal direction, and the load is stretching your material. The other way of imposing the same nature of loading is fixing the sample at the longitudinal end. So one of the longitudinal ends or a given longitudinal end, and then imposing the load along this direction. A simplistic way would be suspending a given material and then hanging dead weights to it. So you suspend a given material and you keep on adding weights to it. It's just like how we used to play on a tree, or when we hang play around with a tree and when we hang on its branches. What we are imposing is a tensile load. So that is exactly what we are doing here. So the branches of the tree are attached to the actual trunk or the stems of the tree, and when we play around with it, when you pull it, what essentially we are doing is we are imposing the tensile load, and which is equivalent to having the branch or being pulled in the two perpendicular or in this direction along its longitudinal axis. It means the same, but in this case what we have is the stem is being attached to the branch, and now we are playing with it and we are pulling it. The same load or the same form of mechanical condition can be imposed if we break this stem and we break this branch, and then one of your friends pulls on the other end and we are pulling in this end. So both these imposes same form of loading. So the simplest way of imposing this tensile loading is in this form, and when you reverse the direction alone, then we end up having a compressive loading. So by imposing or by fixing the longitudinal ends, it is possible based on the direction of the loading to impose either tensile loading or compressive loading. So even though the direction of the load in case of tensile and compressive loading are opposite, both these conditions can be imposed using a similar setup. By fixing one of the longitudinal ends and varying the direction, we will be able to achieve a tensile loading or a compressive loading. Now, instead of fixing the longitudinal length, now it is also possible for us to fix the sample along the longitudinal axis. Now, we don't want to fix the sample at the longitudinal ends. We don't want to fix it at the longitudinal ends, but we want to fix it along the longitudinal axis. So what we mean by fixing along the longitudinal axis is, so this is the sample that we have. Now we want to fix the sample along the longitudinal axis, so we are fixing it this way. So instead of fixing it at one of the longitudinal ends, we are fixing it along the longitudinal axis. So we have fixed this specific section of your sample, and now we are imposing a load here. So we are imposing a load here. So we are placing let's say we are imposing a load along the surface that is not fixed, along the longitudinal surface, or the surface along the longitudinal axis that is not fixed. So that is when we have a load in this direction. So in response to this loading, the material behaves, and that is what we are now focusing on. So that is the loading condition that we are now interested in, and that is the response now we are interested in. Now what we essentially have is all the mechanical conditions that we have considered so far can be easily represented by fixing, or easily imposed by fixing the given material at its longitudinal ends. Now what we want to do is we want to change that condition, and now we are fixing the material or the sample along the longitudinal axis, and we are imposing the stress on its free end. So here we imposed its stress on its free end. So one of the ends that is free, we imposed our stress, be it compressive stress or the tensile stress. Here we have fixed the sample along the longitudinal axis, and in its free surface we are imposing a stress. Now in response to this stress, the material changes its shape. So there is a change, there is a distortion that a material exhibits in response to the specific form of the stress. What we ideally observe is the material adopts a form which is in this nature. So we are fixing a material along its longitudinal axis, and now we are imposing a stress on the free surface that is opposite to the surface that is fixed and in response to the stress there is a distortion that is offered by the material, there is a response that is offered by the material, and this response is of this form here. Now this stress or this load that we impose along the surface of a given material when the material is fixed along its longitudinal axis is what we call as shear load or shear stress. And the response that we observe is a response to this shear load or the shear stress. So by changing the way we fix, the way we handle our sample, it is possible for us to either impose a tensile load, a compressive load, or a shear load or a shear stress. However, depending on the form of the loading condition, the response offered by the material varies. So in this case, what we observe is change in the longitudinal dimension both in case of tensile loading and in the compressive loading. What we observe is the change in the dimension along the longitudinal direction. However, the difference, the response offered by the material in case of shear load or shear stress is quite different. So in order to understand what is this distinguishing response that we observe for the shear load or the shear stress, we will try to compare this response to the response that we observe during the stress and strain. So what we have done is we have considered we are comparing the response offered by the material for two different mechanical conditions. One is the tensile or compressive loading, the other is the shear loading. The difference is that the way we have handled the sample is quite different. One is fixed along the longitudinal ends and one is fixed along the longitudinal axis. Correspondingly, response has varied. Now we want to understand what is the distinguishing feature of this response that we get due to the shear load, and in order to identify this distinguishing response, we are comparing it with the response that we get during, say, tensile or compressive loading. So let us compare the response that we get during uniaxial tensile, to that of shear stress. So in this case you are imposing a uniaxial tensile stress, and in the other case you are imposing a shear stress, and we will compare what is the difference. Now in case of uniaxial tensile stress, what we observe is there is a change in the longitudinal dimension. So principally there is a change in the longitudinal dimension. So there is a change in the dimension along the loading direction. So that is the principal response that we observe when you are imposing a uniaxial loading condition or uniaxial tensile stress. However, if you consider the dimensions of the sample wherein the shear load is imposed, the dimension along the length. So this is the dimension. So it is possible for us to section this entire sample into these elements, and when you consider the length of this section, the dimensional change of this section, there is not much significant change that we observe along the loading direction. So when the shear stress is imposed, when the shear load is imposed, unlike the tensile loading, there is not much discernible change or observable change in the longitudinal direction. So the change in the longitudinal direction, that is a characteristic feature of the tensile loading, is not found here. Now how about the change in the lateral direction? So we saw that whenever there is a longitudinal change in the dimension during uniaxial tensile loading, there is also a lateral change in the dimension that is accompanied during this response. So for uniaxial tensile loading, there is a longitudinal change in the dimension. This is accompanied by a reduction in size along the perpendicular direction. So what we observe is, in case of the uniaxial tensile loading, we observe this Poisson's effect. That is a change in the lateral dimensions. Lateral dimension. A change in the lateral dimension. However, when you consider again the response offered by the material to the shear stress, no such change in the lateral dimension is found. So complete absence of a complete absence of a change in the dimension along the lateral direction, or a complete absence of the Poisson's effect. So under shear loading condition, when you impose, as opposed to a uniaxial tensile loading or opposed to a uniaxial compressive loading, when you impose a shear load, what we don't observe is, we do not observe both, there is no significant change in the longitudinal dimension, and in addition to this insignificant change in the longitudinal dimension, what we observe is there is completely no change in the lateral direction. In the direction perpendicular to the load, there is absolutely no change in the dimensions of the sample. So these are two characteristic features that we have identified for the response under shear loading condition when we compare it with the actual, or when we compare it with the conventional uniaxial tensile loading. No change or no observable change in the longitudinal dimension, and absolutely no change in the lateral direction, no Poisson's effect. So, but what do we observe is, in case of uniaxial tensile loading, when there is a response offered by the material, so this is your initial sample, and after uniaxial tensile loading, the sample has changed its dimension to this. So the black one is before uniaxial tensile loading and the green one is after uniaxial tensile loading. So there is a lateral change in the dimension both along the lateral and the longitudinal dimension, but despite this change, what has not changed is the form or the shape of the sample. That is, when you consider its corners, you find that the angles have not changed. So in this case, we are considering a sample whose corners have the angle, whose corners are perpendicular to each other. The sides of the corners are perpendicular to each other. So these we refer to as the orthogonality, meaning the size or the sides that make the corners. So if you zoom this side out, if you consider the side, so the sides that make the corner is perpendicular to each other, and this we refer to as the orthogonality. So orthogonal sides, we find the orthogonal sides of the given sample even after extending or even after changing its lateral and longitudinal dimension. This orthogonal sides, they remain orthogonal. The orthogonality is sustained. So under the uniaxial tensile loading, the orthogonality is sustained. See, the sides that are perpendicular to each other, the sides that are orthogonal to each other, even after exhibiting a change in the longitudinal dimension and also in the lateral direction, the orthogonality is maintained. The angle between these two is maintained. However, when you consider the change or the response offered by the material under shear stress, you find that there is a key difference. That is, the orthogonality between these two is now lost. The orthogonality between these two sides is now lost. It is no longer 90 degrees. So we have the sides that were initially orthogonal, now because of the shear stress, is no longer perpendicular to each other. So one of the other characteristic features, so apart from no observable longitudinal change in the dimension and no perceivable Poisson's effect, we see that the orthogonality between the sides. So the orthogonality is completely lost when we impose a shear stress or a shear strain as opposed to the compressive or the tensile loading. Now we have identified that there is no longitudinal or the lateral change in the dimensions. However, the only change that we observe is the loss in the orthogonality, the loss in the way these sides are aligned. So in this case, what would be the best way of describing the strain offered by the material? So in case of compression or tensile loading, the strain is exclusively the description of the response offered by the material is largely based on the change in the dimension. So when we want to discuss the response offered by the material under tensile or compressive loading, the way we addressed or the way we describe the response offered by the tensile loading and the compressive loading is by considering the dimensional change along the lateral direction or along the loading direction. So we combined these change in the dimension along the specific directions, and we were able to describe the response offered by the materials along this particular direction. However, since in case of shear stress and shear load, we don't have any change in the dimension both or any perceivable change along the longitudinal direction and also along the lateral direction. So in this case, what would be the efficient way of describing the strain offered by the material? So the efficient way of describing the strain offered by the material should then be based on this particular form of this particular characteristic response offered by the material. So owing to the response offered by the material during the shear deformation, we cannot adapt our conventional description for the strain. We cannot use the dimensional change that we observe along the loading direction or perpendicular to the loading direction. Those description cannot be adapted to describe the strain offered by the material or the response offered by the material for the under the shear loading condition. So our description for the strain or the response offered by the material should be based on the characteristic response offered by the material under the shear loading condition. So this is the characteristic response offered by the material under the shear loading condition. What we essentially observe is, one, the orthogonality is lost. The other way of describing the loss in this orthogonality is the position of the corners have shifted. Now supposing we have fixed our sample at points O and O dash or O prime, and this is the corner A and B. What we observe is the noticeable change in the material in response to the shear load that we have imposed. So we have imposed a shear load, and in response to the shear load there is a noticeable change. The way we are able to notice that change is of course, even though theoretically we can say that the orthogonality is lost, but the way we are able to notice the change is the position of the corner has shifted from A to A prime and B to B prime. So if you consider the sample separately, so this will be your original sample, and after imposing the shear load, the sample will be of this form. So this is our original sample, we have fixed it here, and after imposing the shear load, the sample will be of this form. Now what essentially we have observed is, so this is the original position of the corner, and now the new position is A prime. Now we can use this shift in the position of the corners to describe the response offered by the material. So what we essentially have is, we have imposed a mechanical condition, and this mechanical condition has brought about a response, and it is possible for us to perceive the response by considering the shift in the corners, and the corners have shifted from A to A prime. So therefore, whatever the amount of the shift in these corners is proportional to that of the load that we impose. So if we impose, so P shear is the load that we impose. This P shear, the load that we have imposed, is proportional to the amount of shift that we observe. And this amount of shift has the dimension of the length. And when we want to describe the amount of shift that we observe, and when we want to have a normalizing factor, so this amount of shift is often dependent on the parameters of the sample that we consider. So in the case of the tensile loading, we saw that the amount of elongation was dependent on this parameter of your sample. For instance, in case of tensile loading, the amount of elongation a material offered for a given load, it was dependent on the cross-sectional area, and therefore we were able to normalize it in order to arrive at our description for the stress. So in the same way, we want to get rid of any influence of the material parameters on the shift in the corners that we observe during a shear loading case. So we are imposing a shear load, there is a noticeable change. We are able to quantify this noticeable change by considering the shift in the corners, and this shift in the corners is, we have described it as A prime, and this shift in the corners is dependent on the sample size. So we need to have a parameter, we need to have a way of describing this shift in the corners which is independent of the dimensions of the sample. So in this case, the dimension of the sample that dictates or that influences the shift in the corner for a given loading condition. So for a given loading condition of P shear, the shift in the corners, the shift A prime, is dependent on the length OA. So if the length OA, that is this length OA. So therefore, if we want to get rid of the influence of the dimension, influence of the sample dimension on the response that we observe, then all we need to do is we take the ratio of the shift in the corners that we observe to that of the dimension of the sample, that is L. So we are imposing a shear load, there is a response, and this response we are able to realize it by considering the change in the corners, and this shift in the corners is dependent on the length of the sample, that is OA, the length of the sample. So this length OA of the sample, you can also call it as width, it's up to the way we look at the sample, but here it is dependent on one of the dimensions of the sample. So when we want to get rid of this influence of this dimension of the sample on the response that we observe, we take the ratio with respect to that dimension, and this is what we refer to as. So what we now have done is we have now been able to describe the shear or the response offered by the material to a shear load that is independent of the dimension of the sample. Let me repeat, through this ratio, what we have been able to do is we are able to describe the response offered by the material for the shear stress or for the shear load, which is independent of the dimension of the sample. Response which is independent of the dimension of the sample, so therefore it needs to be referred to as strain. It is no longer elongation or any distortion or anything, because we now have response that is independent of the dimension of the sample, so we refer to that as strain. And since it is the response offered by the material to the shear load, we express this as shear strain. So what shear strain is, it is the ratio of the shift that we observe in the corner. So the shift that we observe in the corners is how we perceive the shear response, and this we have quantified it, and A prime is the shift that we observe in the corners. And when you take this shift that we observe in the corners and take the ratio of it with respect to one of the dimensions of the sample, we end up describing shear strain, and it is the symbol that we use to describe shear strain. In case of the longitudinal strains, or the strain that we get out of compressive or tensile loading, we represent it in terms of epsilon. In case of shear strain, we use delta. So this delta is used to describe the shear strain that we observe when we are imposing the corresponding shear load. Now, when you consider the shear strain that we observe here, in addition to the shift in the corners, we also have noticed that there is a loss of orthogonality that describes the shear strain that we observe. Meaning, when we observe a response offered by the material for an imposed shear load, the response can be described in two ways. One is the loss of the orthogonality. So initially two sides were perpendicular to each other, orthogonal to each other. Now the orthogonality is lost. Secondly is by considering the shift in the corners. So these are two different ways we can describe the response offered by the material for the imposed shear load. Now, the description of shear strain that we have arrived at here is based on the shift in the corners. So two ways of describing the response offered by the material. One is shift in the corners, the other is the loss of orthogonality. Now the description for the shear strain we have is based on the shift in the corner. So it means it is possible for us to arrive at the description that is based on the loss of orthogonality. So when you consider the loss of orthogonality, that is the change in angle from 90 degrees, the perpendicular sides now being no longer perpendicular. Now this is possible because there is an angle established here. So initially the sides that were perpendicular, that is OA, and these two sides were also perpendicular, and they are also no longer perpendicular, and they form an angle now. And if you call this whole angle as say phi, and so if you call this whole angle as phi, so initially the sides OA and OO prime, so that is these two sides OO prime and OA, these two sides were perpendicular to each other. Now there is an angle between OA and O. So there is an angle between A prime, O and O prime. So there is an angle between A prime, O and O prime. So this is because of the shear stress that we have imposed. Now when you compare the new position to that of the old position, when you compare the OA with respect to the OA prime, it is possible for us. So this shift from A to A prime can be described using the theta here. So what we are essentially doing is, now we are comparing the new position with respect to the original position from O. We are not just considering A prime, but we are considering the shift in A from, so the shift in the corners from A to A prime with respect to O. We are just not considering the movement of the corners, but we are considering the movement of the corners from the point O. So therefore, the movement of the corners from point O can be described by the angle theta. So we can use this angle, that is angle A prime, that is theta, to describe the shift in the corners. So when we say the corners has shifted from one position to another position, we can measure the shift and call it as A prime. Or we can also consider the shift by relating it to a point that is fixed, which in this case is O. And when you consider the point that is fixed, there is an angle that describes now the shift from A to A prime. Now when you consider the triangle, that is A, O and A prime. So when you consider a triangle A, O and A prime, this is a right angle triangle. So you have this angle that is 90 degrees. So therefore A, O and A prime. So this triangle here is a right angled triangle. So it means it becomes possible for us to describe A prime, that is the shift in the corners, using the angle theta. So when you take tan theta for the triangle in green, that this tan theta is nothing but opposite by adjacent, that is A prime by OA. So what we are now considering is, instead of considering the shift in the corners just as A prime alone, we are relating the shift to the fixed point of O. And when you relate the shift to the fixed point of O, you end up having an angle, and this angle is a part of the right angle triangle that is highlighted in green. Now what we are attempting to do is, we are attempting to describe this shift A prime using this angle here. So therefore what we have done is, we have taken the angle tan theta, and here the OA is nothing but the length that we have considered before. So therefore the tan theta is nothing but the shift in the corners with respect to the length L. So ultimately what we end up having is, so we have the ratio of the shift in the corners with respect to L, and the same ratio describes the shear strain. So that means the shear strain is nothing but, or it is equivalent to tan theta, where the theta is the shift in the corners and it is linked to the fixed point. So the angle made by the shift in the corners with respect to the fixed point is theta. So therefore that shear strain is tan theta, which is equivalent to the shift in the corners with respect to the length of our sample. So what we have done is, we have considered a new form of loading condition, mechanical condition. This new form of mechanical condition, the material, how it responds to this new form of mechanical condition is different from what we observe under tensile or compressive loading. In this case, there is no change in the longitudinal dimension or along the loading direction, or there is no change in the dimension in the perpendicular direction. So no Poisson's effect, no change in the dimension along the lengthwise. But what we observe is, there is a shift in the position of the corners and there is a loss in the orthogonality. So based on the shift in the position of the corners, we are now able to describe the response offered by the material by quantifying the shift in the position of the corners and taking the ratio of it with respect to the dimension of the sample. We are able to describe the shear strain. So this is what we have done here. And it is also possible for us to consider the loss in the orthogonality, meaning we will be able to take the angle that includes the or that describes the shift in the corners, and using that angle we are able to describe the shear strain. So the shear strain can be described both based on the shift in the corners or the angle that quantifies the shift in the corners. Now again, since we are largely focusing on the elastic region alone, the theta is often minimal. It is not that substantial, it is often minimal, and it is largely close to 0. So when the theta is close to 0, sine of this theta can be equivalent to that of the theta, and cos of the theta under this condition, when the theta is minimal and it is close to 0, is 1. So we have, since our focus is largely on the elastic region and the theta is therefore minimal, in that case sine of theta will be equal to theta and the cos of theta will be equal to 1. So under this condition it implies tan of theta, again sine of theta to that of cos theta will be equal to theta. So under this condition, under the elastic deformation or on the elastic distortion, the tan of theta will be equal to theta. This is nothing but the shear strain that we observe. So ultimately what we observe is it is possible for us to describe the shear strain principally based on the angle that rather quantifies the shift in the corners, the angle that helps us understand or that helps us perceive that a shear deformation has occurred. So this strain is largely equivalent to that of the angle that helps us understand the change in the corners. So we have introduced what a shear loading condition is, and we have seen what are the distinguishing features of the response offered by the material under the shear loading condition. Using these distinguishing features, we now have a unique way of describing the response offered by the material under the shear stress, and this we refer to as the shear strain. And there are two different ways of describing it, and for the elastic region, for the elastic deformation, this shear strain is equivalent to the angular shift in the sides, the angular shift that or the angle that is introduced when we observe a shift in the corners. So with this we will wind this lecture up and we will try to understand. So now that we have arrived at what a shear strain is, we will try to understand what the mechanical condition that we impose, how it can be expressed without the influence of, or how similar to the tensile stress and the compressive stress we can describe the shear condition as well. This we will consider in the subsequent lecture. Goodbye.